you very much to the organizers, Paulo, Professor Croca, John, Sylvia, and all people involved. It's a real pleasure to be here. It's great to see that the different people are producing such interesting results at such a high pace. And it's also nice to see that this is an interdisciplinary community so that we can look at things from different perspectives. And I will today add something from the perspective of the foundations of probability theory. Let me immediately start with Bell's theorem. So this is all clear. You can hear me, right?
Yeah, the sound is good.
Cool, good. So Bell's theorem, you can summarize it in the following way. It says that local hidden variable theories are impossible. Local has a very precise meaning here. So local means subluminal, so Lorentz invariant. That means that non-local is superluminal, so probably contradicting relativity theory. So if you can avoid non-locality, most physicists would do that. In the Walker community, the term non-local is used, but I propose that we use in this context rather the word delocalized. Okay, it's clear that walkers are delocalized after a short time. The walkers, they feel all the boundary conditions even at a large distance. Back to Bell's theorem. So if Bell is correct, then the consequences are very unpleasant, because if Bell is right, it would mean that either nature is superluminal non-Lorentz, so would contain non-Lorentz invariant forces, thereby probably violating relativity theory, or it would be acausal. And acausal, that means that, for instance, in your Stern-Gerlach, when an electron enters, spin would be would assume the value +1 based on nothing. Okay, whether it's +1 or -1, there is nothing, no variable, no property which could explain why it's going up rather than going down. So that means that you have an acausal world, and I agree with Lee Smolin that there seems to be such a fundamental thing, causality, that again, if anyhow possible, you would like to keep it. Very quickly, Bell's inequality is based on three assumptions. So the P, X, Y given A and B is the joint probability of your left and right spin or photon given A and B, and A are the analyzer angles. Okay, and the first assumption that Bell makes, of course, is to try to explain this correlation by hidden variables. So one can be called the hidden variable assumption. Condition 2 or assumption 2 is based on locality, and condition 3 is a so-called measurement independence condition. Okay. It's sometimes also called simply statistical independence, but that's not very clear because 2 is also a condition of statistical independence. So let's keep with measurement independence. So it stipulates that your hidden variables are independent of your analyzer variables A and B. And everyone always assumes it. And for good reasons. In the classical world, this is always the case. Okay. In the literature, people usually justify it by referring to free will. They say, well, it's impossible that my analyzer choices A or B are correlated with the hidden variables. That would be the end of free will, or that would be a conspiracy. These are metaphysical assumptions. So much has been said about free will. People who do research on free will, they would say, well, determinism is rather a good thing for free will. If your brain is doing things in a chaotic, indeterministic way, maybe you have a serious problem. So one way to escape from Bell's conclusion is to assume that against all odds, there is a correlation between lambda and A and B. 3B is just actually the definition of correlation, right? Of course, some of you in this audience would be happy to go another route to escape from Bell's theorem, which is to assume that there are non-local forces, instantaneous or superluminal forces in the universe, and that is a very interesting route to explore too. But then you are possibly in tension with relativity theory. So I will focus here on this possibility condensed in condition 3B. And two speculative solutions, at least two solutions are explored to explain where this correlation comes from. Even if it exists in the macroscopic world, if lambda is a subquantum parameter, things are arguably not as simple. And so one option that has been mentioned in the literature, which actually was inspired by the hydrodynamic walkers and by stochastic electrodynamics by Anna Maria and Lewis, is that perhaps a background field or a pilot wave could create the dependence. The walkers are a super correlated system. Everything feels everything all the time in the system. So that might be a nice condition for having the correlations as in 3B if your lambda are describing the hidden background field. Well, in the walkers, the very real background wave. But this could also happen in the subquantum level, and maybe this could be tested by a hydrodynamic Bell test. This is not a real Bell test. This is a Bell-like test, but it is the thing to do, and I will explain why. So in such a test, what you you're measuring something X, some physical property on two correlated droplets. You need a source of correlated droplets. Why correlated? Because that brings you obviously closest to entanglement. So this is the Bell inequality here, containing 4 factors. Each factor is actually the average product of X and Y. So you need, let's say, 100 pairs of correlated droplets, and you measure X. What is X? X is any physical property. Okay? The only thing you have to do is to divide your outcome space in 2 values, +1 or -1. It can be position, it can be speed, it can be phase, whatever you like. Here in this conceptual scheme, I took the simplest thing that came to my mind, and which is that X is +1 if the droplet is deviated above the line in the middle, and -1 if not. So the measurement happens when the droplet reaches a vertical wall. What you also need in a Bell experiment is a measurement station. And the measurement station needs to interact with the system you're measuring, in this case, the droplets. And the system is characterized by another arbitrary physical property. Here, in this case, I take simply a pin which is pushed into the bath, okay, and which interacts with the droplet and which will at least partially determine the outcome +1 or -1. So you do this for the 4 combinations you have. A and B have 2 values each with 4 combinations. You sum them and you compare this to 2. Everyone expects that since it is a local and classical system, that the Bell inequality will, of course, be satisfied. Now, it is interesting, I believe, to verify this. And there are actually conditions in which I suspect that it will be violated. The whole art of the experiment will be to find one in which the conditions are meaningful. I will explain what I mean just in a second. So you need correlated droplet pairs and measure 4 correlation functions. And what is really important to understand is that a priori, an infinite number of these Bell-like tests can be done on the walkers for any property you choose. Okay, X can be a very wide variety of choices, and it's extremely difficult to say which is the best choice. I think that for the moment, no one can calculate it. So I think that the experiment needs to be done to get a feel for these correlations. Of course, calculations can help something. For instance, you can see that by bringing the left and the right measurement station closer, of course, there will be stronger correlations, right? It will be easier to violate the Bell inequality in certain conditions. I think that the most important point here for this slide is that you can do 2 types of Bell experiments. The static ones, in which you do 4 consecutive measurements, so each measurement for 1 choice of A and B, and you leave the pin, the measurement station, static. That would be interesting. There are reasons to believe that for static experiments there can be a violation of the Bell inequality. but it would not be the real thing. It would be nice. I would suggest to start with that because it's still a very cute experiment, and many people would still not expect it to happen, but actually it can very well be explained, because what you need, what will arise in such a static experiment is a delocalization effect, okay? The left side and the right side, they can feel each other even at the normal subsonic or sonic speed. So that would be interesting. One can learn a lot. There is very interesting physics to learn here, but the real thing would be a dynamic experiment. And for a dynamic experiment, 90% of quantum physicists would expect that the Bell inequality will be satisfied, because this is a local and classic system. What is a dynamic or time-resolved experiment? That's an experiment in which you very shortly do the measurement, and you do the measurement just before the outcome is determined. You can do that here in this case by plunging the pin just before the droplet reaches the left wall in the bath, and by, in this way, determining the result just about in a time which is so that it is impossible that the other side feels it when the measurement is done. You can think of many possibilities. You can think of magnetizing your droplets and activating little a here on the left side. So, for instance, a magnetic field just before the measurement is going to be done, and so on and so forth. So, as I said, we have to be sober. 90% of physicists would think that in such a dynamic experiment, the Bell inequality will be satisfied, but these droplets have surprised us for so many times, and I believe it is worthwhile, more than worthwhile, doing it. We may disagree on whether such an experiment can lead to the violation of the Bell inequality, but I think that we can all agree on one thing, which is that the dynamic Bell test is the ultimate test of the quantumness of the walkers. This is the test you want to use to see how far the analogy quantum hydro really goes. For those who are not experts on Bell's theorem, very short note without explanation. You can separate your lambda into lambda 0 and a part which depends on A and B in a delocalized manner, or a superdeterministic manner, if you like. And what is nice is that in a nonlinear system, a chaotic system, actually infinitesimally small but non-zero delocalized effects can already lead to a violation of the Bell inequality. You can construct toy models, for instance, using this equation, which is the equation describing the angle between a fixed that's the angle of a compass needle evolving between a fixed magnetic field and a rotating one. It's a well-studied system, experimentally, theoretically, and in this case, even arbitrary small delocalized effects or superdeterministic effects can lead to violation of the Bell inequality. So perhaps that is something which gives us hope. That's all I want to say for the moment on this hydrodynamic Bell experiment. Is everyone still with us, Tapio?
Oh, yes, indeed.
Yes.
Nice. Okay. Another test one could do is to verify these correlations here in the real in the real Bell experiment. One could use quickly rotating polarizers. Unfortunately, Marc Fleury told me that this is technologically extremely difficult. That's a pity. For the rest of the talk, I will talk about the second route, which is somewhat better known, to explain where these correlations come from. And this solution is called superdeterminism. And the most famous proponent of such a theory is a Nobel laureate, Gerhard Hooft. So actually, superdeterminism could be simply termed determinism, I believe, but it simply takes determinism seriously. It says that, well, our choices A and B are ultimately neurobiological, so physical events in the brain. Any physical event as causes, as Lee Smolin just also expressed, so causes or variables, properties. The causal tree starts at the Big Bang, so in principle, everything is correlated to everything, and therefore, 3B would be correct. There would be a correlation dependence between lambda and AB. Mathematically, it's well known that superdeterministic hidden variables theories can predict the quantum correlations of a Bell experiment, and the first to prove that was Brahms in '88. yet belief in such theories remains in the quantum foundations community very modest. Okay, and as I said, there are good reasons to why it's not a popular theory. Maybe from a physical point of view, the most relevant one is that, well, it seems impossible to construct a theory that allows you to predict, what will be your next choice of A and B. Okay, if your lambda are, for instance, the ab initio, the ultimate parameters of the theory of everything, even if, well, it seems difficult to construct such a theory which would allow you to predict what is going to be the correlation between lambda and AB, or let alone what will be your choice of your analyzer angle A or B. Now, in this talk, I want to give indirect support to this position, superdeterminism, starting from probability theory. And I will show that this hypothesis of superdeterministic hidden variables can answer a series of questions for which the orthodox position, which is, of course, there is no such thing as hidden variables, remains entirely silent. So this rings again a bell with what Lee Smolin said. When you do science, you believe the theory or you adopt a theory which allows you to answer most questions. I would summarize it in that way. First, a small remark, as I will use superdeterminism in a slightly broader sense than often done in the following. Superdeterministic hidden variables can be both deterministic, in which case your quantum variable x is a function of lambda, or stochastic, in which case the conditional probability x given lambda is defined. So actually, for me, superdeterminism is equivalent to the assumption that hidden variables exist, or the hidden variable hypothesis. The variables can be stochastic or deterministic. Interestingly enough, the mathematical proofs can actually only be given, or usually be given only for the purely deterministic case, but I will not present this here. Several of them are known. So here is question one that I would like to answer is the following: how to interpret statistical correlations in the classical and quantum domain. So for some reason, I have to stop, I think, and reshare again. For some reason, let me see. Can you see this, Paulo?
Oh, yeah.
You can see this?
Okay.
That's no problem. We have lots of time and
Excellent.
the information is the more important.
Great. So here's the first question, which was in 1993 remarked by Kolmogorov, the father of modern probability theory. He says the following in his small book. In consequence, one of the most important problems in the philosophy of the natural sciences is, in addition to the well-known one regarding the essence of the concept of probability itself, to make precise the premises which would make it possible to regard any given events as independent. This question, however, is beyond the scope of this book. So we know that the definition of independent variables, x and y, is that their joint probability factorizes. And so Kolmogorov is asking here, how can we know in advance when two variables are correlated or not? Is there anything that determines this? What could we use to not have to guess or to measure it? So in general, in real world situations, there's no rule. The only way to be sure is to experimentally verify for whether the joint probability factorizes or not. But even if no rule exists, of course, one often intuits correctly whether events or variables are dependent or not. How do we intuit that? Well, surely because of our intuitive understanding of whether events are causally connected. Whether one event is determining the other one. If we think that, well, there's a causal link somehow between x and y, either direct or because there is a common cause, Z, then we expect correlation. And this is actually usually attributed to Reichenbach. He went a little bit further and he said that, so we all know that there's correlation if X and Y are in direct causal relations or they have common causes. And in the latter case, Reichenbach conjectured there is a Z, there is a set of variables Z, which if you conditionalize on them, you can defactorize, you can factorize your joint probability. Okay, and Z is a complete common, a complete common cause. In short, correlation is explained by hidden causes or hidden variables, hidden or not. Sometimes they're not hidden. And this principle has been verified countless times, many times in classical macroscopic systems, but is generally believed not to hold in quantum systems precisely because of Bell's theorem and other no-go theorems, but this is clearly neglecting superdeterminism. Interestingly, Reichenbach's principle can be proven in the deterministic case, and this has recently been done by people in Oxford and in the Perimeter Institute. I will not give the proof here. You can prove a similar theorem, which says that, well, if correlation can actually be undone by factorizing on the causes, on the variables that make X and Y causal. Okay, so this is one question, what is correlation, which can only be answered, at least in the quantum case, if you assume the existence of hidden variables. Second question is how to interpret the central limit theorem, or more precisely, why are there so many stochastic phenomena, both in the classical and quantum realm, described by a Gaussian distribution. So Gaussians are, of course, ubiquitous in quantum mechanics too, including for pure states. There's a whole series of famous mathematicians having contributed to the CLT, the central limit theorem, many Russians. And it is often called the unofficial queen of probability theory. So in many applied probability books, you see people, describing the beauty, the order that this theorem brings into the randomness of probabilistic system. So here is the CLT, any probabilistic variable that is the average, so the weighted sum of many independent variables has a normal Gaussian distribution independently of the distribution of the contributing variables under very wide conditions. So as you remember probably from your applied probability course, books typically present the theorem as an explanation of why the Gaussian is so ubiquitous in the physical world. And the explanation is straightforward. People say many phenomena are the average of many unobserved independent phenomena, and that's just a direct reflection of the math of the CLT. But for my concern, this is highly irrelevant, but because this needs again causal terms, hidden or non-hidden, extra variables in the interpretation of probability. Because what is said here is that X is a function, is a sum function of additional variables. So again, this key ingredient of probability theory as a theory of the physical world are most naturally understood in terms of an underlying causal reality, in other words, hidden variables. Again, the no hidden variable assumption does not help to understand the CLT. And here's problem T, that's a serious problem, or the most serious problem, even if this is a matter of taste. And that is, are there degrees of freedom that could unify quantum mechanics and relativity theory? And can we say at least something qualitatively about such variables that could do the unification? So I use unification here in the usual sense, like for instance, electromagnetism unifies electrodynamics, optics, and so on. By the way, string theorists might disagree with this term of unification, but I'm not sure what they mean with their unification. So I'll stick to the meaning that is used also, for instance, by 't Hooft and by, I would say, all remaining physicists. Now, this is a big problem because general relativity theory and quantum field theory are believed to be mutually incompatible, at least in regions of extremely high mass and small dimensions, such as in black holes and the Big Bang. And this incompatibility actually parallels the standard interpretation of Bell's theorem. Indeed, this theorem shows that quantum mechanics cannot be derived from underlying deterministic theories, such as general relativity theory. More precisely, deterministic and local, so Lorentz invariant degrees of freedom that can describe general relativity cannot describe quantum mechanics as an irreducibly probabilistic theory. So it seems that the no hidden variables verdict of Bell is again a direct obstacle to the unification program. But as I said in the beginning, and as is well known, there is an escape route from Bell's no-go verdict, which is superdeterminism. So let's go a little bit deeper into superdeterminism. Most people reject it, but actually only on the basis of metaphysical reasons. And if you take determinism seriously, the classic argument is the following, then, well, A and B are also causal parameters determined by some causes. They are in a causal network. These causes have their causes until you reach the Big Bang. So on this interpretation, the lambda are the degrees of freedom of a theory that describes the Big Bang or the universe shortly after it. In other words, it is a theory of everything, right? And these degrees of freedom are common causes of X, Y, A, and B, because everything starts from there. Everything is causally related to the Big Bang. So this is the view that people like 't adhere to. Here the lambda are part of a theory of everything which would describe the Big Bang. More precisely, a theory of everything that would really describe even your choices of your analyzer settings. So probably this is an elusive theory. We will never be able to construct it. This seems to be a God's privilege. Now there's a problem with this view. Okay, if everything is correlated to everything, why then do we see stochastic independence all the time? This is discussed in the specialized literature. For instance, if Alice and Bob choose without a pre-established plan their analyzer angles, then of course these two, well, A and B are decorrelated, and you can measure that. Now the solution to this conundrum is following idea, I believe, that this is to note that the superdeterministic correlations may exist in principle in an elusive theory of everything, but are unmeasurable in practice. So this idea can be illustrated in well-known chaotic systems. For instance, in billiard collisions, that's a deterministic system, which becomes chaotic if you introduce a small uncertainty in the initial positions of the cue ball. So we know how this system evolves. And with my collaborator, Vitaly Nikolaev, we studied the correlations in this system. This is another example of a system that's massively correlated. Everything is actually correlated to everything, well, under certain conditions. And you can show that the ball properties are massively correlated, but that this correlation can only be detected by high precision probability measurement. In other words, if the number n of trials is very large. Of course, every probabilistic measurement has an experimental error, which decreases with the number of trials. So actually, it is only normal that your superdeterministic correlations between lambda and A and B cannot be measured, neither calculated. So the next important question is then, but is all next generation physics then impossible in a superdeterministic universe? Can you never, in a local manner, explain the quantum properties? And well, this is a slide which I would like to have some comments on, because this is a rather new idea. I didn't have the time to think much about it, let alone to discuss it. I think that you can construct theories and explain quantum properties because there could be an intermediate level theory, a level 1 theory, which has local hidden variables and which explains your quantum properties A and B, because this correlation between lambda A and B can be mediated through lambda star, which are the common causes between lambda xy and AB. Lambda star are the ab initio hidden variables, so they are correlated to everything, and they can explain the correlation between lambda and AB. So arrows here indicate causal connections. Variables can be part of theories of a different level, and the thick arrow symbolizes how realistic effective theory of quantum gravity, for instance, or a local hidden variable theory a la pilot wave theory could explain quantum mechanics. So you have the ultimate theory of everything, which is not accessible to us, and then you have effective hidden variable theories, perhaps a pilot wave theories, or you have an effective quantum gravity theory, which still introduces new variables, local variables, explaining x and y, but these should then be, I suppose, probabilistic variables. Let me explain this a little bit better. In any case, these variables should not be part of the inaccessible ab initio theory. So here is a tentative intermediate conclusion. If this is correct, then superdeterminism would be a actually metaphysical principle that has a huge importance because it would guarantee us the well-foundedness of next generation physics. To make this a little bit clearer, I think we can use the analogy with thermodynamics. That is a high-level theory, but and we know that it can be derived from mechanics, even if we do not know the values of the mechanical variables. But there is an intermediate theory, statistical mechanics, which can explain thermodynamics. Okay, so this reduction between theories is done all the time in physics. Your x could be a thermodynamic property. If you know the partition function, we can calculate these thermodynamic properties. So Z takes here the role of lambda. Well, in this case, for instance, you can calculate the probability of x given Z. Usually it's just a delta function. So this, as an analogy, might explain what I'm pointing at. So in conclusion, this is my second last slide. Once more, determinism, or the hidden variables hypothesis, offers an answer, I believe, to the question of problem 3. The question is, are there variables which can unify quantum mechanics and relativity theory? Well, quantum gravity should do that job, right? And quantum gravity is a theory that describes the Big Bang. It should involve effective variables describing the Big Bang, but Bell's theorem points exactly to these degrees of freedom as a possible solution of problem 3. The correlation between lambda and AB is explained in this way, since these degrees of freedom are old enough, lie far enough in the past line cones to be conceivable as common causes both of quantum variables and freely chosen analyzer angles. So the no hidden variable assumption seems to offer no answer to problem 3. Rather, it leaves Bell's theorem as an obstacle to the unification. This is my last slide. There are three questions that can be answered by superdeterminism, in other words, the hidden variable hypothesis, while the no hidden variables hypothesis remains silent for them. Here are the 3 questions. We know since Browns that any superdeterministic theory can reproduce the quantum correlation. So if we have a superdeterministic theory, we can reproduce quantum mechanics, so we can answer all the questions that quantum mechanics could answer. But superdeterminism allows to answer actually a series of other questions. There are others, but these are the most relevant. So this is then what this suggests to me, that we should adopt superdeterminism maybe as a unifying principle in physics and consider probability theory as a theory revealing determinism, in other words, causality. And if you would say this in a slogan, it would mean something, well, it would say that probability theory, that's my slogan of today, probability theory is a physical theory. As a physical theory is a theory of causality, actually. And I also suggested that superdeterminism can be seen as a principle justifying the quest for effective local hidden variable theories, maybe pilot wave theories. Thank you very much for your attention.